Welcome, everyone. Nicola is going to tell us about coinvariants of metaplectic representations on moduli of abelian varieties. And it's my pleasure to introduce him. Take it away, Nicola.
Thank you very much, Flor, for the invitation to be here. And thank you all for connecting. It's a great pleasure to connect with you all and have the chance to present this project. I'm going to discuss this work which plays on the interplay of infinite-dimensional Lie algebras and geometry of certain moduli spaces. In the beginning of the talk, I will mention some motivations. Then I will be fairly elementary in reviewing some infinite-dimensional Lie algebras, and that will finally lead to the application of this study of infinite-dimensional Lie algebras to the geometry of moduli spaces. So you will be able, so if you would like to know more, the paper is on the archive as of last year. You can find here the archive code. And very briefly, let me start by saying what was my original motivation. The idea was to start from the construction of vector bundles of conformal blocks on curves and their moduli spaces, and see to what extent that construction can be generalized to larger moduli spaces. So specifically moduli spaces of abelian varieties. So that is the goal of the project, and that's going to be the final result, which will appear in the last 5 minutes of the lecture. But how do we get to that stage, right? So traditionally, vector bundles of conformal blocks and spaces of coinvariants have been constructed using vertex operator algebras, which have been tailored specifically for to work with along with the geometry of algebraic curves. And so if you want to go from algebraic curves to abelian varieties to a different type of geometric object, necessarily one needs to make some changes. And this is what I would like to motivate. And I would like to basically review a little bit the history of conformal blocks, what is really needed, and how one can generalize from curves to different type of geometric objects. All right, so I'm going to mention here in the next 10 minutes, perhaps a little bit of, I will drop some keywords and I will mention some constructions of conformal blocks. If you are very familiar with this is great. If you are not, just treat this as a motivation for what's going to be next. So the idea is to start from conformal field theory. What is that? Well, for me today, this is a recipe that allows one to construct vector bundles that I will denote like here, blackboard V, over blackboard V, over moduli space of curves MG. MG is the moduli space of objects C, which look like this, is a Riemann surface or an algebraic curve of geometric genus G. So for instance, here in the picture, this is the case where the G is equal to 2. And the recipe proceeds as follows. It takes as an input an object from quantum algebra, and so specifically vertex operator algebras that many of you in the audience know and love very well. So V here. What is very important here with this V is that it carries an action of the Virasoro. So this action of the Virasoro plays an important role in the geometric side, and that's what I will emphasize next. All right, so you start with the VOA V, with a vertex operator algebra V together with the action of the Virasoro, and this construction provided by conformal field theory produces a vector bundle which depends on the V. So this is blackboard V of the VOA V on the moduli space of. So how I would like to say a little bit more in details how this construction works. The idea is that the vertex operator algebra is often an infinite-dimensional vector space with additional richer structure. And so in order to engage the full algebraic features of the VOA, one needs to make an extension from MG to a larger modular space, which in fact is infinite dimensional. And this is called the modular space MG, is denoted MG hat, which is a modular space of triples consisting of an algebraic curve C as before. But now I'm introducing 2 more objects inside the triple. One is a P, which is a point inside the algebraic curve. And then there is T, which is a local coordinate at the point P. Now one can always vary the local coordinate at a fixed point P, and you can vary this in infinitely many ways. Then the moduli space MG hat of such triple is infinite dimensional. And so it provides an infinite dimensional space which lies above the moduli space MG of algebraic. This map here, this horizontal map, is just a forgetful map that to a triple CPT assigns just the curve C. All right, so why there is some convenience. So there is a price to pay here that you need to step to infinite dimensional, but geometrically there is a convenience. And the idea is that this space MG hat by doing this operation, you remove all static structure. All right, so this is a complex analytic manifold, and so it's an object which is much easier to deal with. And on this space, on MG hat, it's here that one first construct a vector bundle, which is denoted blackboard V hat. And this vector bundle is defined as follows: the fiber over a point. I will describe the fiber over, say, a point CPT in this moduli space. The fiber consists of the following. You take the V, the vertex operator V here that you have fixed as an input. Is the same V that works for all the triples. And what you do is you quotient by the action of a specific Lie algebra, which has been constructed from V and from the geometric input of C minus P, the complement of P on the algebraic curve C. Right? So the idea is that the geometric point in the moduli space allows you to construct a specific Lie algebra that takes as an input both the geometric input and the VOA V. And this Lie algebra has an action on the VOA. And when you do this quotient, this is how you construct the moduli space of. This is how you construct the space of covariance. It's a vector space assigned to this triple. And what is interesting is that this construction works well in families. And so it gives rise to a moduli, to a vector bundle, over the space MG hat. Right. So this is roughly the construction, and the vector bundle V hat is called the vector bundle of coinvariants over MG hat. So this is how one starts the construction. And what is interesting is that this vector bundle then descends to a honest vector bundle on the moduli space MG of curves. So you can remove the point MT. Well, how can you do that? Well, because the construction is equivariant with respect to the group of change of the coordinate T and with respect to the point moving on the curve. All right. And so by equivariance, this construction descends, allows you to construct a vector bundle on the moduli space of curves of genus G. Now, what is interesting is not just the existence of this vector bundle, but the fact that this vector bundle has a distinguished property, which is the following, namely, it carries what is called a projective action of the tangent sheaf of MG hat. So this is an action of, you can think about the tangent sheaf as being a sheaf of Lie algebras, and the sheaf of Lie algebras acts on the vector bundles V hat. And this, one more time, this action is equivariant, and so it descends to an action of the tangent sheaf of the modular space MG on the vector bundle blackboard V. So this is why this construction is so important and has been used so much in geometry. You don't get just vector bundles, but you have vector bundle with this distinguished property, namely a projective action of the tangent sheaf of the base. And this is also called sometimes a twisted D-module structure, right? Those two, the projective action of the tangent sheaf of the base or the twisted D-module structure are equivalent way to think about this property. So to give you some ideas about this. So for if you have a vector bundles, then you can think about, if you have vector bundles of finite rank, then you can consider their Chern classes. And you can ask, to what extent does the projective action limits the Chern classes, imposes constraints on the Chern classes? And it turns out that the presence of a projective action tells you that all the Chern classes of the vector bundle are polynomials in the rank and the first Chern class alone. Right? So all of the higher Chern classes are determined polynomially by the rank of the vector bundle and the first Chern class. So this is in a certain sense telling us that if you have vector bundles with a projective action of the tangent sheaf of the base, you have some constraints on the structure of the vector bundles themselves, and yet the collection of all such vector bundles still enjoys a lot of important properties. You still have some flexibilities in order to have some surprises, right? In order to obtain vector bundle that still has a lot of topological information about the base variety. So maybe few words about, how do you get the projective action? You get the projective action. I will spend the second half of the lecture, just the next half of the lecture, just discussing how this projective action is determined. And everything, in a nutshell, everything follows from the original Virasoro action on the vertex operator algebra. So that algebraic input is the key in order to lead to this important geometric property
Nicola,
of the resulting vector.
A question. This construction
Please.
works independent of what VOA you choose. You can do it for any VOA, or are there extra conditions on your VOAs?
Correct. There are some conditions on the VOA. So, for instance, you want to argue that the action of the Virasoro, the elements say. So you want to argue that the elements of negative degree are always. Let me say it this way. So basically, it depends what kind of properties you want on the vector bundle. So if you want vector bundle to be of finite rank, right, then there are some constraints that you want to put on the VOA, right? And these constraints. So for instance, you want perhaps like a C2 cofinite VOA or a rational VOA, and some of these hypotheses can be weakened. Right?
Thank you.
Definitely. Please, anybody, if you have questions, feel free to unmute yourself and ask. So basically here, the idea is that right from this geometric input, we care very much about VOA with the Virasoro action because they lead to geometric construction, specifically vector bundle with a projective action of the tangent shift. I would like to say one more geometric interpretation for this for the projective action of the tangent shift. And the idea is the following, described in this diagram here at the bottom of the page. The idea is that this specific property allows you to identify infinitesimally nearby fibers independently of the path connecting the base points. What this means is the following. If you take 3 base points A, B, C, 3 points on the base variety, and if you consider the fibers over these 3 points, let's call them VA, VB, VC, you can consider the projectivization of these fibers, all right? So you get these 3 projective spaces. The projective action of the tangent shift of the base, what it gives you identification pairwise of these 3 projective spaces in such a way that these identifications commute, all right? In such a way that this diagram commutes. And this is another way of saying that the identifications are independent of the path that you choose connecting the 3 base points A, B, C. All right. So this is another way, geometric way to think about this projective action of the tangent of the base. So all of this motivates a careful understanding, a careful study of this tangent shift itself. All right. So once we know that, once we are looking for this type of vector bundles, then it is interesting. We would like to understand better, how to describe specifically the tangent shift to MG and perhaps starting from the tangent shift to MGN. So in the next part of the lecture, I will focus on how to describe this specifically, the tangent shift to MGN. Now, the tangent shift of a complex manifold should be a shift of Lie algebras. So the question is, which Lie algebras do we need for this description? All right, and surprisingly, this is extremely, the Lie algebras that are required were very well known in the algebraic literature. And so one starts specifically with the following, with the Witt algebra that many of you know very well. So the Witt algebra is defined as the following Lie algebra. This is the Lie algebra of derivations of the ring of Lorentz series in a formal variable T, right? So this is as a vector space, it's an infinite dimensional vector space. You can consider it together with the t-adic topology. Okay, it's a completed vector space with respect to the t-adic topology. So an arbitrary element looks like an infinite sum with coefficients AP in C, and derivations LP, where the derivations LP are traditionally defined in this way. So it's minus t to the power p plus 1 partial. So this is a vector space of derivations. And where is the Lie algebra structure? Where here is the Lie bracket. The Lie bracket is defined just as the commutator of two derivations. And if you do the computations here with LP and LQ, you get precisely P minus Q times L over P plus Q, right? So this is a honest infinite-dimensional Lie algebra. And you can think there are two ways of thinking about it. So algebraically, you can think about this as being the derivation of the ring of Lorentz series in a formal variable t. And geometrically, another way of thinking about it is as the Lie algebra of vector fields on the punctured disk. What is the punctured disk? It's just the spec of the ring of Lorentz series in a formal variable, right? It's whatever geometric object has C as this as the ring of regular function. All right, so what we're talking about is, you take a disk, you remove the central point, and you end up with one fed point. Now this is this is, in order to proceed further, I need to introduce one additional Lie algebra, which perhaps needs no introduction in this seminar, but just for those of you who are more on the geometric side, I would like to let me briefly mention it. So there is a Virasoro algebra, which is the central extension of the Witt algebra by a one-dimensional space. So it is central, which means that the additional vector blackboard 1 that we introduce commutes with all the LPs. And the Lie bracket is defined as follows. So the Lie bracket now of LP LQ is the pullback of the Lie bracket from Witt, which is what we have seen here before, plus an additional contribution. And the additional contribution here is a multiple of the new vector blackboard 1 that we are introducing. And this multiple is given by the following expression. There is 112. 112, this is just a scalar, and it can be rescaled, just a matter of a convention. And then we have p cubed minus p. P is specifically this index over here. And then there is a Kronecker delta, which is either 1 or 0, depending on whether p plus q is 0 or not. Right? So this is the Virasoro algebra, and as many of you know, this is the up to scaling. There is only one central extension of the Witt algebra, and is given precisely by the Virasoro. Now, all of this is well known in infinite-dimensional algebras, and it comes from it goes back to at least the 60s, I would say, from studies of Gelfand and Fuchs. Specifically, at the time, Gelfand and Fuchs were interested in the cohomology of infinite-dimensional Lie algebra, right? And so they were studying the cohomology of Witt, and they computed that the two cocycles of the Witt algebra, in fact, it consists of a one-dimensional space, and is spanned precisely by the two cocycles that gives this central extension, this specific two cocycle, right, up to a scalar. And so there is only this is the proof that there is only one-dimensional central extension of Witt up to scale. So all of this to say that this is part of mathematics that was motivated by algebra. But in fact, what I would like to argue is that there is a lot of geometry hidden here in the picture. And this became clear in the 80s, specifically by the following theorem, which is due, so we're talking about 1988, and the following theorem, which is due to simultaneously to two independent set of authors. One group consisted of Arbarello, De Concini, Katz, and Procesi, and the other group by Bellinson and Shechtman. And what they show is that the Witt algebra acts transitively on the moduli space that we have seen at the beginning, MG hat. One more time, this is the moduli space of triples of type CPT, where C is an algebraic curve, P is a point in the algebraic curve, and T is a formal coordinate at the point P. All right, what does acting transitively mean? It means precisely the following. It means that there exists a surjective map of Lie algebras from Witt to the tangent space to MG hat at any point CPT. right? For any point CPT in MG hat, you have this surjective map of Lie algebra. All right, so this is extremely powerful, because what it's telling us is that while Vit seemed to be a fairly innocuous Lie algebra, in the sense that it's a Lie algebra of derivations of derivation of the Ling of Lorentz series in a formal variable T, or if you want, is the Lie algebra of vector fields on one fat point on the puncture disk. While that seemed to be fairly innocuous, well, this theorem tells us that, in fact, the Vit algebra encodes all tangent directions to moduli spaces of curves, encodes all the first order deformations of algebraic curves in moduli. So this is extremely important theorem from the 80s, and this is the statement about Vit, and there is also a companion statement about the Virasoro, namely, as the Virasoro was the one-dimensional central extension of Vit, correspondingly there is a geometric counterpart, and if Vit acts transitively on the moduli space MG hat, then the one-dimensional central extension V will act transitively on a one-dimensional central extension of the moduli space. What is that? Well, naturally is a line bundle over the moduli space of curves. And which line bundle? Well, actually there is only one up to tensoring. And this is the Hodge line bundle. This is line bundle that over any point in CPT, it gives the top wedge power of the global sections of differentials on the algebraic curve. And so the statement is saying is that Vit acts transitively on the base variety, and then the Virasoro will act transitively on the Hodge line. Right? And to make this more precisely, one needs to say, how the central element in V will act on the fiber. The central element will act by a scalar multiple on the fibers, and the specific scalar multiple is 2. It's a factor of 2, acts by a factor of 2. This 2 is determined by the factor of 112 that we picked in the definition of the Virasoro. So if you vary this 112, the 2 will vary accordingly. But what is important is basically the quotient of, so the product of these two should be 1/6.
Nicola, sorry, I have another
Please.
question. So from the
Please.
relations of the Virasoro algebra that you have there, it seems like you fix your central charge to be 1. Is that correct?
Yes, it's correct. So correct. So for here, I'm just thinking about Virasoro abstractly, right? So if you want, if you can think about it.
You're calling 1 the central element. Okay, sorry.
Correct. For me, this is just an abstract vector. So you can think about the Virasoro as acting on itself with central charge 1. Sure.
I see, but the transitive action is independent of the central charge. So it's of the Virasoro algebra as a Lie algebra.
Correct.
Is that correct? Okay,
correct.
Thank you.
Correct.
Thank you.
It's of the Lie algebra. Correct. No, I'm not thinking about this as a BOA. Correct. Thank you. Great. So So here we are in the 80s, and
and there's a question in the chat.
Oh,
sorry, Nicola.
Yes, definitely. Thank you, Jonathan. Yeah. So CPT are those are triples, and C is an algebraic curve of genus G. P is a point on the algebraic curve, and T is a formal coordinate at the point P. Right. So this is how we think about this MG hat. So G would be the genus of C. So excellent. All right, so this is the story about curves, and in a certain sense, this is the key result. It's a result from the 80s, and since then has been used so many times, specifically because it provides an explicit description to this tangent space, the tangent space to the moduli space MG hat. And equivalently, by descending by the action of the change of coordinate T and moving the point P on the curves, it provides it subjects on the tangent space to MG, to the moduli space of curves of genus G. But so now the question is, how do we move forward from here, from this picture? Well, I would like to mention 2 ingredients. First ingredient is one that is very well known to algebraic geometers. It's something that algebraic geometers learn in their school, and is a result that goes back to 1913. We are talking about here. We are at the beginning of the School of Italian Algebraic Geometry with Ruggiero Torelli, that tells us the following. Basically, there is an inclusion of the moduli space of curves of genus G into the moduli space, into a larger moduli space, namely moduli space of abelian varieties of dimension G. The map is obtained as follows. To an algebraic curve C, one assigns the Jacobian of the curve C, which is defined as the moduli space of degree 0 line bundles on the curve C. And it comes naturally with a principal polarization denoted theta. All right, so explicitly, this is defined as a quotient of a G-dimensional vector space, complex vector space, by a lattice of integer rank 2G. So it's a one-dimensional. So it's a G-dimensional torus together with a principal polarization. And so this is a result of Torelli. So what is important here is to remark on the difference in dimension of these spaces. So while the dimension of MG grows is 3G minus 3, so grows linearly in G, the dimension of the AG grows quadratically in G. So as you increase G, the difference between two will be wider and wider. And so naturally, having in mind this extension, this Torelli map, one naturally is a natural question to ask is to what extent do constructions that are known on MG, to what extent do they admit a generalization to this wider moduli space, the moduli space H. And so specifically going back to the construction at the beginning of today's lecture about the vector bundles of coinvariants, to what extent can one construct a vector bundle of coinvariants more generally on AG? So this is what I would like to focus on for the second half of the lecture. And in order to do that, necessarily we need to do something here. There is some work that has to be done. So the construction on MG of vector spaces of coinvariants started by considering this MG hat, the moduli space MG hat, which was an infinite dimensional moduli space, which allowed to better engage the algebraic structure of the DOA. And is there a counterpart for the moduli space of abelian varieties? And well, there is, and the answer is provided by a result from the 90s from Arbarello de Concini. This is a paper that I discovered accidentally, in fact, while I was doing a search literature. And I was so happy when I found it out because it provides precisely the tools that are needed in order to carry forward the program that I mentioned at the beginning, the idea of the program of constructing coinvariants on moduli space of abelian varieties. So what is the result? Arbarello de Concini in 1991 showed that, in fact, there exists an infinite dimensional manifold AG hat, and this moduli space AG hat sits precisely into a commutative diagram. So if before we have seen MG hat lying above MG, this infinite dimensional moduli space MG hat lying above MG, and considering the Torelli map that includes MG inside AG, what Arbarello de Concini do, they construct this new moduli space AG hat sitting in this commutative diagram together with an extended Torelli map so that MG hat is included inside their new moduli space AG hat. All right, so what is this moduli space specifically? Well, I will not be able to say too much about the construction today, but I would be happy to do afterward if you would like. For the moment, let me just say that this is a moduli space itself and parameterizes extended abelian varieties. What does that mean? Well, in a nutshell, what this means is that those are extensions of abelian varieties, group extensions, by the following group. This is the group of Taylor series in a formal variable T with 0 constant term, and modulo equivalence, all right? Isomorphism. And similarly, together
Nicola,
with please.
Could I just ask a quick question? Maybe we'll come back to it at the end, but just out of curiosity, is it different than taking the abelian variety marked by its theta divisor and taking a parameter at the generic point of the theta divisor?
Yes, it is different than that.
Okay.
Thank you. So great. So that would be the natural thing to do, right? But in fact, that's not how it works, and the construction is fairly more involved than that, right? And so the construction was motivated, in fact, by what they call the Krichever construction. So we are talking about here the 90s, and there was a lot of emphasis on the work of Krichever that provided specifically within the realm of KP equations and provided connections with Stato-Grassmannian. So their construction was very much motivated by those results. What I can say right now is that right, so we need to extend abelian varieties by this group, all right? And moreover, there is a companion vector space. So for every S for the classical vector space AG, there is a universal family, usually denoted X lower G. Arbaro de Concini also construct an extended universal variety and extended universal family, and they call it X hat lower G. Now, the best way to say what these moduli spaces are is to focus on their first order deformations. And so specifically, we would like to return to the theme of a few minutes ago with given by the following theorem, which provided a uniformization of the moduli space of curves, right? So if V2 was the Lie algebra which acts transitively of MG hat, can we is there similarly a description of the moduli space AG hat and XG hat? That's the question I want to answer next. And the idea is to introduce some more infinite dimensional Lie algebra, which will replace the role of bit. Right, so the question is, what about the infinitesimal bridge, right? What about the first order deformations at any point in this moduli space? And the idea is the following. So what was V2 one more time? V2 was the Lie algebra of derivations of the ring of Lorentz series in a formal variable T. And the idea is that now, if you only consider the derivations of the ring structure of the ring of Lorentz series in a formal variable T, you only get the derivations, you only get the first order, the tangent directions to the moduli space MG. If instead we want to stick to this larger moduli space, all right, we want to include more tangent directions, so we want now a larger Lie algebra to consider, right? And so considering just derivations of the ring structure will not do it. What we should do, the idea is to still think about this space, this ring, the ring of Lorentz in a formal variable T, but not as a ring anymore. So shed the ring structure and consider rather a weaker space, a weaker structure on this object, on this algebraic object. And what is the weaker structure? The weaker structure is the structure of a symplectic space, right? So what I'm going to do next, I'm going to define a symplectic structure on this. How? Well, we need a symplectic form, and so let's start with a bilinear alternating form. And this is a form that may look very familiar to many of you, right? This is precisely the Tuco cycle that defines the Heisenberg algebra, right? So given two elements of two Lorentz series and formal variable T, you consider the following pairing, which is minus the residue at T is equal to 0 of FTG. So it's easy exercise to see that this is bilinear, it is alternating, right? And this leads to the Heisenberg algebra. So we should in principle check also the Jacobi identity, but that is automatically satisfied because the result of these two forms is always a constant, and constant always by this form, they always commute with everything else. They pair with 0 with everything else. And so this is to say that this is a two-nilpotent Lie algebra. So the Jacobi holds trivially, and this is how one gets to the Heisenberg. For some of you that might not be, they might feel a little bit not at ease with this definition. What I'm doing here is I'm quotienting the Heisenberg by the identification of the constant term and additional the central element. All right, so so we have the Heisenberg algebra. Great. Now this form is degenerate. It is degenerate because, as mentioned, it is easy to see that f pairs to 0 with everything else if and only if f is a constant. And so in order to create a non-degenerate form, what we can do is just take the Heisenberg and quotient by the constants. Right, so just let's remove all the constants, and this way we obtain H prime, which is now which becomes a symplectic space together with this form. Right? Does the symplectic space make sense? All right.
So once we have the symplectic space, what we can naturally do is consider a symplectic algebra. All right. And what is this? This is the Lie algebra of elements of this form, all linear maps X from H prime to H prime, which are continuous with respect to the t-adic topology, verifying this constraint. Right. So this constraint is exactly what you get when you consider the Lie algebra of the symplectic group, the group of automorphism that preserves the symplectic structure. Right. So if you do that exercise, then this is starting from the group of symplectic automorphisms preserved preserving the symplectic structure. Then by differentiating, you get precisely this constraint, and this is the definition of the symplectic algebra. All right, so we arrived at this important Lie algebra here, and this is what I would like to focus on for the remaining of the lecture. It may seem fairly abstract, but in fact, I would like to convince you that it is very easy to deal with, and its elements can be described fairly explicitly in the following way. So there is, you can consider H prime, one more time, this is the space H prime, all right, is Ct modulo the constants in T. And you can consider the second symmetric power of H prime. All right, so those are just the tensors of two elements inside H prime. And the statement is that the symplectic algebra, in fact, equals an appropriate completion of this second symmetric power. All right, so first I would like to convince you that the second symmetric power lies inside the symplectic. How? Take an element AB, which is supposed to be A times B. This is supposed to be A times B or A tensor B, if you want, an element in the second symmetric power of H prime. So I'm taking the product of two elements in H prime. And I want to argue that A times B acts on H prime. How? In the following way. To little h in H prime, it assigns the following elements on H prime. You do the pairing of A with H times B. So that's a scalar times B plus BH times A. All right, so ultimately you get a scalar times B plus a scalar times A. So this is the action of AB on H prime, and it's easy to see. So this realizes AB as a linear continuous map of H prime, and it's easy to see that AB satisfies the symplectic condition. So one obtains an inclusion of the second symmetric product of H prime inside the symplectic algebra. The last thing to verify is that one gets an inclusion this way, and finally one obtains an identity by doing an appropriate completion. The completion consists of allowing possibly infinite sums of terms like that, right? And you have to complete with respect to the t-adic topology. There is only one meaningful way to do that. So I hope this makes sense. Please let me know if you have questions. And I would like to convince you that, in fact, please.
Again, what is S squared bar? S squared bar and parentheses.
Oh,
H
this one. Yes.
Yes.
So S2 of H prime is the second symmetric product of H prime. So it's just the product, all symmetric products of elements in H prime. And then the tilde, it's a completion. So I'm allowing possibly infinite sums of products of elements of H prime. Right? Let me give you an example for an infinite product that we are allowing. This is an infinite product that we are allowing. Right? So I would like to explain this map here. This is called the oscillator representation that many of you might have seen before. So from the Witt algebra that we have seen before, which is topologically generated by the elements LPs, there is a natural inclusion of Lie algebras from Witt to the symplectic algebra, which is defined as follows. To every LP, one assigns 1/2 of the infinite sums of t to the power I times t to the power minus I plus b. Right? So this is what is usually called the Seagal-Sugawara representation, right? And this is what it allows to determine, for instance, you can complete, this induces, there is an enhancement of this, which gives you an inclusion of the Virasoro inside the Heisenberg VOA. This is how you argue that the Heisenberg VOA is a conformal, is a vertex operator, right? And what is important here is to realize that to LP, one assigns this infinite sum. As you see, this is an infinite sum of products of elements of H prime. All right, so each one of these products is inside S2 of H prime, and the infinite sum will be inside this completion. Right, so it's an honest element of SP of H prime. So it's easy to say that all these images satisfy the symplectic condition. So in fact, this is a well-defined map from the Witt algebra to the symplectic. All right. So one more time, this was clear from the algebraic perspective. And I should say that, from the algebra perspective, in fact, this is not the only map. There are many different maps from Witt to the. There are infinitely many maps from the Virasoro to the Heisenberg VOA. There is a one-parameter deformations of such maps. But in fact, this is specifically the maps that goes from Witt to the symplectic, right? And I would like to give you now, let's return to the geometry. I would like to give a geometric interpretation of this map. And this is precisely one of the many beautiful results from Arbarello de Concini. What they say is that, in fact, the symplectic algebra acts transitively on the moduli space AG hat, on the moduli space of extended abelian variety. So the symplectic algebra is the Lie algebra that replaces the Witt algebra with respect to the geometry, passing from the geometry of curves to the geometry of abelian varieties. And moreover, if you are interested in the extended universal abelian variety, then the Lie algebra to consider is the semi-direct product of SPH prime and H prime. Right? Semi-direct product with respect to the natural action of SPH prime on H prime. All right, so those two statements are exactly the generalization of the statement saying that Witt acts transitively on the moduli space MG hat. Right? So what it's telling us one more time is that the symplectic algebra encodes all first order deformations at all points in the moduli space HE hat. And similarly for this second step. And finally, to wrap up this part of this central part of the lecture, I would like to bring up this diagram that includes all the statements that I mentioned so far. So we have two diagrams here. There is a top diagram, which is a diagram of infinite dimensional Lie algebras, and there is a bottom diagram, which is a diagram of moduli spaces and corresponding line bundles. So we am combining here the various results from Arbarello de Concini, Katz-Procesi, Bellinson-Schechtman, and Arbarello de Concini. So we have Virasoro as an extension of Witt, and this acts transitively on this portion of the bottom graph, right? In the sense that Virasoro acts transitively on the Hodge line bundle, and Witt acts transitively of MG hat. We have seen how Arbarello de Concini give us this inclusion of MG hat into a larger moduli space AG hat, and SP of the symplectic algebra acts transitively on AG hat by this theorem over here.
So I'm sorry, I missed MPH prime is some sort of central extension, one-dimensional central extension of SPH prime, or what is?
Very good. Thank you. Yeah, I didn't get there yet. Are you referring to MPH prime?
Yes.
Great. I didn't get to that yet.
Okay, great.
Yes. Just one second. I will get there soon. I just noticed that I hope the audio works well.
I'm receiving the audios from the computer instead of my earplugs. All right, great. So right. So I want to clarify that the symplectic, by this theorem, the symplectic acts transitively on AG hat, and moreover, the oscillator representation, which is the map here we see at the top of the page, including Witt inside the symplectic algebra, in fact, is after quotienting is the differential of the extended Torelli map. All right, so we see algebraically, we see the extended Torelli map algebraically precisely encoded by being determined by the oscillator representation. And now let me refer to the MPH prime. So this is a Lie algebra that was referenced in the paper of Arbarello de Concini. And yes, thank you, Michael, for the question. It is a one-dimensional central extension of the symplectic. And in fact, there is a Cartesian diagram here. You can think about the Virasoro as being the pullback of the metaplectic of the metaplectic central extension of the symplectic, right? And I'm writing this in red because there are some details that I had to fill in my paper, and specifically what I had to fill in was the study of this metaplectic Lie algebra, and argue that the metaplectic Lie algebra is the Lie algebra that acts transitively on the Hodge line bundle on the moduli space of abelian variety. All right. So what I had to do is basically study the cohomology of this symplectic Lie algebra, argue that the space of H upper 2 of 2 cocycles is one-dimensional and is generated by, after multiplication, by a single 2 cocycles, which determines this extension. And you know, the central element of the metaplectic algebra acts by multiplication by 2 on the fibers of this Hodge line bundle on the moduli space of extended abelian variety. And similarly, there is a story here also for the extended for the universal abelian variety. As mentioned here in this theorem of Barbarelli Concini, there is a symplectic algebra semi-direct product with H prime, which acts transitively on this moduli space. And there is also another interesting story here, which I have clarified in the paper. Namely, on the universal abelian variety, there is a canonical line bundle, denoted capital C. What is this line bundle? This is a line bundle that reduces to twice the principal polarization on all the fibers. And this line bundle, in certain sense, also has a counterpart in this infinite dimensional picture. Namely, there is a Lie algebra, very natural Lie algebra here denoted tilde U lower 2 of H, which will act transitively on this line bundle in the sense that the central element of this algebra acts by multiplication by -2. Few seconds, I want to say what is this Lie algebra. In a certain sense, this Lie algebra determines everything in this picture. What is it? Basically, you start with the Heisenberg Lie algebra. You consider its universal enveloping algebra. This is a filter Lie algebra, and you look at the terms of degree less or equal than 2. It's a specific property of the Heisenberg algebra that it's filtered. The filtration of the universal enveloping algebras are Lie algebras themselves. This is due to the fact that the commutator results in a constant which commutes with everything else. And so the terms of degree at most 2 in the universal enveloping algebra of the Heisenberg form a Lie algebra themselves. And one consider an appropriate extension, which again, we are allowing possibly infinite sums. We are completing with respect to the t-adic topology. So this space, which might seem fairly mysterious, in fact, can be broken down in very simple terms. If you are looking at terms of degree at most 2, what do you have? You have the quadratic terms. Those are precisely the terms that give you the symplectic Lie algebra. You have the linear terms. Those are precisely the terms in H prime. And then you have the constant term, and this is exactly the central element here, which gives you the central extension. Right. So this Lie algebra here, you know, if you quotient by the terms of degree 1, then you obtain the metaplectic, and vice versa. There is also an inclusion of the metaplectic and as the terms of degree 0 and 2 inside this Lie algebra. And it turns out that this Lie algebra acts on has a geometric counterpart, which is this line bundle, this canonical line bundle on the extended universal abelian variety. All right, so I like this theorem very much because it gives this this dictionary to go from the world of infinite dimensional Lie algebras to the geometry of moduli spaces and line bundles on them. Now, what I would like to do is I would like to use this in order to construct sheaves on these moduli spaces, right? So in the first part of the lecture, I argued how important it was to know that the Virasoro, that the Vit acts transitively on MG hat, and thus the Virasoro acts on the Hodge line bundle. So morally, the projective action on spaces of coinvariants is determined by the action of Vir on the VOA that it is used in the construction of coinvariants. So by this perspective now, if instead I want to construct something on AG hat, then I need to replace the Virasoro with this larger Lie algebra, the metaplectic Lie algebra. And that's exactly what I'm going to do next. So this is the construction that I propose. So one more time, we start from an object from quantum algebra, this time, not necessarily a VOA, but I want a representation of the metaplectic Lie algebra, right? I want to replace the action of Virasoro with an action of the metaplectic. From the geometric side, I want to replace a point in MG hat with a point in AG hat. This is an extended principally polarized abelian variety. It's a point little a inside AG. And so
Nicola, do we
please.
have a really good list of VOAs that emit such representation?
Yes, so certainly you can take all Heisenberg VOAs and all lattice VOAs. So there is a specific condition. Basically, you want to make sure that there is an action of you can think about this as being so this is a central extension of SPH prime, and remember how the SPH prime can be thought as a completion of the product of H prime. All right. And so, for instance, there is as you basically you want to make sure that you have an action of product of two elements of the Heisenberg in such a way that if you have a B positive I and B lower positive I and B lower negative I, this product should act locally nilpotently. So this is always true for Heisenberg VOA and lattice VOA.
So maybe VOAs that have a Heisenberg field will be fine, maybe?
The Heisenberg?
A Heisenberg field, so not just the Heisenberg VOA, but a Heisenberg field.
I think so.
Okay, gotcha, thanks.
Thank you. And all right, so the geometric input, this is the geometric input, this is the algebraic input. With this input, what am I going to do? Well, first, I'm going to get two outputs. The first output is a Lie algebra. Namely, we talked about the fact that SPA acts by Arbaro de Concini. We know that the symplectic algebra acts transitively on the modular space, which means that meets a surjective map of Lie algebras to the tangent at AG hat to AG hat at the point A. And as such, that would be that we can consider the kernel of this map. The kernel of this map is this Lie algebra, which depends on the point A that we have picked. In other words, this SP lower A is the stabilizer of SP at the point A, at the point little. It turns out, so this is naturally defined as a Lie subalgebra of the symplectic algebra, and it turns out that the metaplectic, which is a central extension of the symplectic, splits over SPA. So we can think about SPA as a Lie subalgebra of the metaplectic itself. The action of the metaplectic via this inclusion induces an action of the SPA on V. And so what I can consider is a quotient of V by the action of SPA. So now I've constructed a vector space which depends on V, on the input V, but the V is independent of A, but the quotient depends on A because this Lie algebra and the action of V depend on the point. So there is a little bit work to do. So I've defined this here now point-wise, and with little care, one can show that this construction works well in families. And so here it leads to the following theorem. The spaces of coinvariance, these spaces of coinvariance give rise to quasi-coherent shift Blackboard V hat on AG hat. And now, careful, it's not just important that it's a quasi-coherent shift, but what is important is that it carries a projective action. That's the property I was after, right? From following the thread from the beginning of the lecture, I wanted to make sure that whatever I construct has an action, a projective action of the tangent shift of the base. And this is induced precisely by this action of the MP. Right? And so this is a quasi-coherent shift on the modular space AG hat. And if naturally we are interested to see to what extent this story descends on AG, and it turns out that under some natural assumptions, this is the condition floor that I mentioned more appropriately about the action being locally nilpotent of certain elements. You need this condition in very far. So there is some technical condition which is very fine in several interesting cases. And with this technical condition, these spaces of coinvariance descend on honest quasi-coherent shifts on the modular space AG of principal hyperpolarized abelian variety. So from the infinite dimensional modular space AG hat, we can go down to the finite dimensional H. And finally, let me mention how there is also a similar property, a similar story over the extended universal abelian variety and the universal abelian variety descending from the infinite dimensional set. All right, I encourage you to ask me questions, but before perhaps ending, I would like to mention a few open. So this is the statement. This is what I wanted to obtain from the beginning, and I was very happy when I arrived at this stage. Mostly thanks to all the work of Arbello De Concini and previous work that I mentioned that allow me to carry over this construction. Now the good news is that we have this quasi-coherent sheaf that has the projective action on the tangent sheaf of the base. But what are some desirable next steps? I'm being careful here in saying quasi-coherent because why not coherent? Well, it turns out that in general, the rank of this sheaf is infinite. All right, so I do not have finite rank in general, right? And I would like to compare this with the situation of spaces of covariance at curves, where in fact, in several interesting cases, as mentioned before, perhaps when the VOA is C2 cofinite or rational, the rank is known to be finite. And so natural question would be, how can we still preserve the property of having a projective action, but at the same time becoming finite rank? And so the idea is that SPA, the Lie algebra that I'm quotienting by in this construction, is the minimum Lie algebra you can quotient by, is the minimal Lie algebra you can quotient by, so that you have an action of the tangent sheaf of the base. Right? A projective action on tangent sheaf is the same thing as an action on tangent sheaf on the projectivization of the space of covariance. And so the idea is that basically the problem would be, how to enlarge this Lie algebra that I'm using to a larger Lie algebra so that the quotient becomes finite dimensional. So the idea would be to consider a larger Lie algebra so that by quotienting by this larger Lie algebra, the rank drops down to finite rank. And the inspiration should be perhaps given by the story on curves. On curves, the SPA was the stabilizer at any point on AGN. And on curves, the stabilizer was the vector fields on the curve C, which are regular away from the point P. This is what I mean by this notation, calligraphic T of C minus P. The vector fields on the curve C, which are regular away from the point P. So those are the stabilizer of the Witt uniformization of the moduli spaces of curves. But in the definition of coinvariance on curves, one doesn't quotient by this Lie algebra alone, but rather one quotient by a larger Lie algebra, this curly L Lie algebra that was featured at the beginning of this talk. It's a much larger Lie algebra, which includes not just the geometric input, but also the input from quantum algebra, the VOA. And so the idea is that there should be correspondingly a larger Lie algebra, which doesn't depend only on the geometric input, doesn't depend only on the stabilizer of the geometric point, but also should include, more generally, the specific representation of the metaplectic that you are considering. And finally, one last question. In the story of curves, it was important to see how a construction on the locus on smooth curves gives rise to a construction on the locus of stable curves when possibly one allows singularities. And over the stable curves, how one has a factorization theorems relating the fibers of these vector bundles on singular curves to the fibers of the corresponding vector bundles on the components of the normalization of the non-vector. And the idea would be that whether perhaps there is a similar story that leads to various compactification, perhaps a second Voronoi compactification of moduli spaces of abelian varieties. All right. Thank you all for your attention. And please, I welcome any talks or comments or suggestions. Thank you.
Thank you so much, Nicola. Let me stop the recording so people are more comfortable asking questions. Thank you so much for the wonderful talk.
Thank you, Flor.